close to now. Okay, so we can start, I guess. So we talk about the principle of equivalence. Okay, so sorry for the slight delay in starting the lecture. First, before we even start, so technical, right? So we will not have meeting this Thursday, obviously, Israel's Independence Day. And then also next week I will be away, and also Akshay will be away, so there will be no lectures. So we meet again in 2 weeks' time. So Sunday, not next week, but the following week. You will get the problem set, so you don't need to worry, so you have some things to do while you're waiting eagerly for the next lectures. Okay, recap on what we did. So this is the starting point of the discussion about general relativity. And the starting point was the weak equivalence principle, which was so equivalence principle. We said that there are two equivalence principles. One is called the weak. This is really Otto-Fosch's experiment. We chose that the inertial mass is equal to the gravitational mass. The way that particles, any particle, reacts to gravity is identical to the way it reacts to other forces. And that led Einstein to introduce what's called the strong equivalence principle, or the equivalence principle in short, which says that at every point in arbitrary gravitational field, it is possible to choose a locally inertial coordinate system such that within a sufficiently small region of the point in the question, the laws of physics, laws of nature, take the same form as in an accelerated Cartesian coordinate system. So in simple words, the weak equivalence principle simply says that mg is mi. And the strong equivalence principle says I don't care really what is the gravitational field that I'm in. Whatever point I have which is subject to a gravitational force, I can always find a locally inertial coordinate system that is a freely falling system. Right? I'm here, I feel the force of gravity. Right? Otherwise I would just fall down. But you know, I could be falling down. Could be jumping out of a plane and falling down. Could be an astronaut orbiting Earth. Right? The astronaut does not feel the force of gravity because he's orbiting Earth. Right? So he's in a free fall. He tries to measure g, he will not be able to do that. Of course, locally. As we demonstrated, if I want to jump out of a plane, here I can find a locally inertial coordinate system in which I don't feel gravity. And if my friend in Australia wants to do exactly the same thing, she could do the same thing. She would have a local inertial coordinate system, but it will not be the same locally inertial coordinate system. That's why it's a local count. Right? That's the first conceptual thing. to discuss. And then we showed that this automatically, without doing anything really, no more than what you do in elementary school, we showed already there is one direct measurable consequence, and that is the gravitational redshift. Again, this example, two people on a gravitational field, but different location, deeper in the potential well. And for these two people, we showed that the proper time is not going to be the same. So this is A, Ayala, and this is Benny. We find out that delta tau Benny is delta tau Ayala 1 minus GH over C squared. To first order, everything we did was first order Taylor expansion. So the only difference is that Benny and Ayala are not at the same depth inside the gravitational potential well of the Earth. Right, and the way we did that was to assume that rather than being subject to the gravitational force of Earth, let's assume that they are both inside the spaceship, which is accelerating at acceleration A, which is equal to G. Which we can always do, essentially because of Roche. Right? Alternatively, that means that if there is a crest of light, it is emitted from a distant star. So there is a star here. And we are, with the telescope, we are observing the star, and the star emits light. It's on frequency, the star. Then the observed frequency is not the same frequency. The frequency of the light. We assume that we're at infinity relative to the star, so the gravitational potential of the star is 0 for us. It is an E star 1 minus delta phi over C squared, which is V star minus GM over R C squared. Of course, it's the first order approximation, but it's quite good. As we showed, for most objects of interest, maybe except neutron stars, or everything that happens really, really close to black holes, which we did not define yet, but we will define them, of course, later, the correction is quite small. It's of the order of a few percentage, so it's okay to take a Taylor expansion. We're not making a huge error. Yes?
If, for example, gravitational field where observer is standing is the same as gravitational field of the star, there will be no any gravitational redshift, right?
Yeah. I mean, in fact, if we are observing the sun, okay, let's say we look at light from the sun. So light from the sun has to go out of the gravitational potential of the sun,
Yes.
then enters the gravitational potential of Earth.
Yes.
So when it enters, it will be, of course, the opposite. So we have to take that into account. But as I showed, practically the gravitational potential of Earth makes a very, very small correction for astronomical observation. It's not something which we can neglect when we talk about other experiments such as GPS. But when we talk about astronomical observations, it's of the order of 10 to the minus 9, so it's very small. While for stars, we're talking about much bigger, still small, but much bigger, anywhere between 10 minus 6, 10 minus 4, 10 minus 1, depending on which type of object we're looking at. Okay? But yes, of course, we have to consider that as well. But it's a small, practically, gravitational potential of the Earth is very, very small. It makes a very, very small correction from most astronomical practicalities. Okay, so this was a simple consequence of that. Then we went into started to dirt our hands with the math, right? And dirt our hands with the math, it's still worth maybe making this drawing. So we said, okay, let's say this is a star. We said there is like a parachute jump. Jumps. It doesn't matter. And there is really a coordinate system which is non-accelerating, so it's really falling with him. That's fine. And then we said it's quite important that everything we did in special relativity holds for that coordinate system. And now we wanted to ask a very general question, which is how does the motion of this object, particle, person, whatever, photon, would look like in an arbitrary coordinate system, arbitrary, not necessarily freely falling. Right? And this is a freely falling. And this is arbitrary. Not freely falling at all.
But flat, right?
I didn't say it has to be flat. I said arbitrary. It doesn't have to be flat. Completely general.
Okay.
That's a nice thing. And even in the example I gave you in the last few minutes, it was a flat, but you can select any coordinate that you want. I can give it to you as homework, or we may do a little bit of sketch here, right? You're used to certain ways of describing flat space, right? You know cylindrical coordinates, spherical coordinates, maybe you know others. Everything falls under this category. I said completely, what we're doing is completely general. Okay? That's the nice thing about what we do here. It generalizes many things that you've seen in your math or even physics courses, right? This is the arbitrary, we're using a different color. So we said that the motion of better. And we said if we write down these coordinates as psi, right? Psi alpha, this would be x mu. Different color. Then we know that the proper time tau squared is minus 1 over c squared. Beta alpha beta d psi alpha d psi beta. And we know the equation of motion of the particle in the freely falling system. Without any external forces acting on him, the equation of motion is d u, we write this a capital, alpha over d tau is d squared psi alpha over d tau squared is equal to 0. Of course, there are 4 equations here. And when we wanted to express that in any arbitrary coordinate system, we simply use the chain rule. To do that, write down d tau squared is minus 1 over c squared, and beta alpha beta d psi alpha over dx mu, dx mu, sorry, that's a partial derivative. You have to take all the directions. D psi beta over dx mu, dx mu. And that this was defined as minus 1 over c squared g mu nu dx mu dx nu, where g mu nu, we define it as eta alpha beta d psi alpha over dx mu d psi beta over dx mu. That's really what defines our new coordinate system, right? Old one is the freely folding one, So it's quite easy. But now we have a new one which is arbitrary. X mu and x nu are choice. And that defines the metric. Then we realize that the equation of motion in this new coordinate system, the equation of motion becomes d squared x lambda over d tau squared is a minus gamma lambda mu nu dx nu over d tau dx nu over d tau, where gamma lambda mu nu is defined as dx lambda over d psi alpha d squared psi alpha over d x mu dx mu. This is known as the metric tensor. This is known as the affine connection. Of course, alpha here is a dummy index. Right? I could write any Greek letter that I wanted to, because anyway I'm summing over alpha. It appears twice. One is an upper, one is a lower. Right? So it doesn't matter. Just have to sum over alpha. And this has, well, depending on the dimension of the problem, right, in an n-dimensional space it will be n cubed different components. Yeah? Yeah. Alright. Now everything I did was just a mathematical manipulation. I did not touch anything here, there's no physics really here. It's completely mathematical manipulation, which essentially says, okay, now I'm having a coordinate system which is arbitrary, so it's not a freely falling. In the freely falling, I saw no force. So this was no acceleration in the particle. It's just freely falling. But in this arbitrary coordinate system, which is not necessarily freely falling, but could be accelerating, think of it as fictional force if you want. Doesn't matter. I do see this is acceleration. The particle is accelerating. This is an acceleration term. And the acceleration depends on the coordinates, but mainly on this affine connection. Okay? So in a way, this affine connection, my interpretation, this is now a physical interpretation to a completely mathematical statement, would be of a associated with the gravitational force. Somehow. One more word about the name affine connection. We will mention it, but I don't know if we'll have time today, or likely only in the next lecture. Why is it called connection? What is it connecting, really? Remember when we spoke about vectors, I stressed the fact that vectors are attached to a single point in space-time. That is crucial when the space-time is not flat. So I cannot really compare vectors which sit in different locations in space-time, which I refer to as manifold. I have some sort of manifold, I have a point P, I have another point Q, and I set a tangent vector space which I call TP. This would be, of course, TQ. And if I have a vector that belongs to TP, it can talk other vectors that belong to TP, in the sense that I can add them in a linear way, etc. Right? They form a linear space. But if I have another vector in TQ, these two vectors cannot talk to each other, because they live in different spaces. But very shortly, I will need them to talk to each other when I need, for example, to calculate derivatives. And the way to do that, we're going to see, is called the affine, is via this affine connection. So it's called connection because it connects different points, nearby points, on a manifold. So that's just for the origin of the name. Okay. Now this equation has a name. This equation really describes a freely falling particle motion of freely falling particle in arbitrary coordinate system x mu. Alternatively, this can be written as d u lambda over d tau minus gamma lambda mu 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 mu, where u mu is dx mu over d tau. It's a definition. If it's a photon, it's the same, but I cannot simply use tau. I have to specify a different parameter. So it will be a d squared x lambda over d sigma squared is a minus gamma lambda mu dx mu over sigma dx mu over d sigma. This equation, being so important, has a name. This is called the geodesic equation. What does the geodesic equation describe?
Moving along geodesic.
Which means what?
Equation of motion.
What?
Equation of motion.
Of what? They have any equations of motion. If I travel from here to Beersheba, I'll travel various roads, right?
Straight line.
Straight line, essentially, right? I'm going to show that shortly, right? This is the equation of motion of a particle that has got is not subject to any forces, except from gravity, because gravity is not a force.
So if
But it is generally true. This will be an equation we're going to show. It's going to be an equation of straight line in any arbitrary space. Yes.
for example, particle has a charge,
Yes.
there will be also some additional terms
Yes.
in that equation.
If there is a, let's say, if there is an electric field,
Yeah.
the particle is charged, then I have to put here. It's not going to be equal to 0. It's going to be subject to the electromagnetic force. So I have to put here, instead of 0, F alpha, right, representing the 4 vector of electromagnetic, 4 force.
Mhm.
Right? Of course, this will translate here as well.
But not the same way, not just plus F alpha. to the
Well, that
right-hand
depends.
side.
That depends on the structure of F alpha.
Ah, okay.
It could be. If it's a constant force, it could be constant. Okay. So that is the. Let's take it. Keep it simple. It's already confusing. Why keep it more? Why confuse even more? Then I did 2 more things. I managed to prove to you mathematically that there is a mathematical connection between that and that. Right? So we showed, I'm not going to repeat the entire calculation, but I showed you that if we know the metric, we can calculate the affine connection. So the affine connection is derived directly from the metric. Show that gamma sigma lambda mu is 1/2 g mu sigma d g mu over dx lambda plus d g lambda mu over dx mu minus dg mu lambda over dx mu. So it's not that straightforward, but at the end of the day, if you know g, then you can simply take this derivative, first derivative, calculate its inverse, and you get all the components of the affine connection. In fact, it's quite easy, right? You put the inverse of G, you have one upper index, so you put the inverse of G with that upper index and another parameter. And then you're taking the derivative with that upper index and one of the lower indices with respect to the x of the other lower indexes, right? So G nu over dx lambda, and then G nu lambda over dx nu, and then minus G nu lambda with respect to that x nu. So it's a mathematical connection. It's just a simple algebra. Well, maybe it is simple. It can be confusing because there's a lot of Greek letters in it, but at the end of the day, it's the only thing we really did here was to use the chain rule. And the definitions here, there was nothing more than that. So there's no reason to go through. And I said that this term actually specifically has another name, and that's called the Christoffel symbol. Which is also denoted by sigma lambda mu with the curly brackets. Now there are some subtleties here that we don't really need, but I can just mention it to you. So why the same thing has two names? So it's not exactly the same thing, but practically it is the same thing. In principle, you can define an affine connection even without a metric. We're not going to need that because we're not going to deal with any spaces that do not have a metric. But you could have an affine connection without a metric, and then you can define other things using the affine connection, but not a metric. The Christoffel symbol, why it comes from, it basically tells you, if you look at these derivatives, what would be the affine connection in a flat spacetime? Minkowski or Euler. What do you get here?
Simply one.
1?
Zero.
0. Everything is 0. Right? Try to take a derivative of G. G is just constants, 1s or 0.
Yeah.
If you try to take the derivative of G with any coordinate, you get a 0, right?
Mm-hmm.
The 1 over the r is 0, right? So basically, in a way, that Christoffel symbol tells you how much you deviate from flatness. In a way, that's one of the things. What I saw that some people say, okay, that you can it's the same connection as the vector and the components of the vector, right? The affine connection and the Christoffel symbol. Practically, at least for this course, you don't really need that, because for us, we're dealing with simple spaces. Okay, simple spaces. And nothing too fancy, like, you know, you can think of all sorts of interesting spaces. Mobius strip, if you know what it is. It's one of, but we don't need that in the realm of GR. Maybe more sophisticated theories will need that, but right now it's just basic introduction to GR. So just know that. It's enough for you to know that it exists, and for any practical purpose, it's the same thing for us. Nothing, I gave you an example, a very simple example. I said, okay, it looks confusing. You're going to have a homework set today so that you can start working out to make it slightly little confusing to you. But in reality, after you get used to it, you see that it's not more difficult than other things you already did. It's just much stronger tool than everything you've seen. And I gave you a simple example, which is what happens if I try to write down simple, flat, two-dimensional Euclidean space, but in r theta coordinate, Euclidean space written in r theta coordinates. So of course the space remains flat, we don't touch the space. But if you look at G mu nu, right? So the simplest way of getting G mu nu, if you get confused, is just write down the line element. ds squared is dr squared plus r squared d theta squared, and then G mu nu would be dr theta 1 0 0 r squared. So you're saying that now you can take the derivative, but the only thing that will give you a non-zero will be g theta theta over the x1, the r. Give you a 2r. So this is something which you can easily calculate, and you get that there are 8 different components here, but most of them will be 0 except from 5. Except from 3, sorry. So gamma r theta theta is minus r. Gamma theta r theta is gamma theta theta r is 1 over r. Simply use that. One thing which again you automatically see is that because of this definition, or from here it doesn't matter, you see right away that gamma is symmetric in exchange of the lower 2 indexes. So gamma r theta is always equal to gamma theta r for the same symbol here. Simply practice it and you see that it's not that frightening. Questions?
So Christoffel symbols are not exactly a deviation from the flatness, because for this example,
No, this is just look at the definition.
Yeah.
Just look at the definition, right?
Yeah.
If the g has some dependence on the coordinates, it will give you a non-zero Christoffel symbol.
Yeah.
And it's the same as the affine connection because of that proof that I proved to you last lecture. All right. Now, basically, we derived the geodesic equation as equation of freely falling particle. You said, and rightfully you said, that this is also a straight line in a way. In reality, what we say, it's the shortest path. Right? The shortest path between 2 points. Right? So shortest path is really the generalization of the concept of a straight line from flat space-time into any arbitrary curves. Right? And remember this, I should have brought it with how many of you flew to the US or to North America, to America? Didn't have this chance?
Okay.
Not yet, okay. How many of you flew? Somewhere, okay. Now, you saw these maps, right? Now they give these maps, right? We have this like a map, right? This is America, whatever. This is Europe, Africa, whatever, Asia, whatever you fly, right? And then you're saying we are somewhere here, right? This is Tel Aviv, and this will be America, let's say. And when you're flying, what is the trajectory that the airplane is doing?
On the flat, it's like line, straight line, but
yeah,
on the surface,
in reality, it will look something like that, right?
Mm-hmm.
Okay, it doesn't make sense. Why would it go like that and not just go a straight line? Well, it does go in straight lines, obviously. And of course, no company will take you just a tour to see theirs. They have one interest, which is to save money, which means that they want to minimize the amount of fuel that they consume. So they go in straight lines. Sometimes they have various restrictions, like no flight zones or dangerous zones, etc. Typically, they will go in straight lines when they can, right? So, what is the equation of a straight line? Geodesic.
Yeah.
So that's what we're going to do now, right? You've seen that actually, in a way. Where did you see that? Where did you discuss like straight lines?
Maybe analytical.
Analytical mechanics, right? In Lagrangian formalism. Mm-hmm. So what we're going to do now, basically repeating the thing you did in Lagrangian mechanics. I'm just going to show you that from the variational principle, which right, everybody here took Lagrangian mechanics, right? I don't have. Yeah, we get the same geodesic equation. So let's do that. So the subject is called the geodesic equation. And variational principle. Like about exclusive deterministic principles in this course. Okay. So what we consider in general is called a test particle. What does it mean, a test particle? What is a test particle?
It's like a test charge, but now with mass.
Yeah. What makes a...
I'm asking what will happen if I put a particle.
Yeah, but what does it mean, a test particle? What's the formal definition?
It does not affect the surrounding and
Exactly, right? So I can neglect the mass of the particle, the gravitational force, gravitational field of that specific particle. Right? So I put a small particle in a big gravitational field, and basically I can neglect that. Of course, what they mean by test particle, that depends on the problem at hand. I am a test particle, or an airplane full of passengers is a test particle relative to Earth. The Earth is a test particle relative to the Sun. That's right. For every practical reason, when I make calculation of the gravitational field of the Sun, I can neglect the gravitational field of the Earth. Well, except for when I'm close to the Earth, the Moon. So we have a test particle, no forces except gravity. So no electromagnetic forces or anything else that you can have. So the claim is that in the absence of external forces, the particle takes the shortest path between points A and B. What does it mean, shortest path?
shortest in time.
What time? Proper time, of course, always proper time. So, shortest path, that means extremizes, minimize, the proper time between the points. Again, this is generalization of the concept of a straight line. This is called geodesic. It's a generalization of straight lines. This path is known as geodesic. And the equation of motion is the geodesic equation. So we're actually going to do it twice. First, we're going to do it in special relativity, so flat space-time, and then we're going to do it in general relativity. questions? Okay, so one equation of motion of a free particle in special relativity from the variational principle. So we want to extremize tau. So tau, right, from A to B is what? Integral from A to B of the tau. So how do we do that? We have 2 points, A, B. This is the tau. We want to choose a parameter along the particle's path. And we write it down as integral from A to B, d lambda. Actually, it's not from A to B because now I have to specify what is the lambda, the lambda of B. And the tau is what? It's a minus 1 over c squared, eta alpha beta, d psi alpha over d lambda, d psi beta over d lambda, power 1. How do we, now we want to find a parameter, so we want to find a word line that will minimize tau. How do we do that? It goes back to your analytical mechanics.
Take a variational derivative.
Very good. So use the variational principle. Take a small change. Delta psi. Lambda. And then simply write down Lagrange equation of motion. And write Lagrange equation of motion. So you can think of that as the Lagrangian, right? And that's the dynamical variable. Care about. And d lambda would be here the time. So Lagrange equation of motion, d over d lambda of what?
L to the
dl over d psi alpha over d lambda plus dl over d psi alpha is equal to 0. You know that, right? Both.
Yeah.
With classical mechanics. And L is what is written here, right? So L is minus 1 over c squared eta alpha beta d psi alpha over d lambda d psi beta over d lambda. 1. So, what is the L over the Xi?
Zero.
Yeah. L does not depend on Xi. Just on the derivative of psi. Right. So now we need to take, so this goes to 0. And then we're left with, so I don't care about the minus here because it goes 0 anyway. So I have a d over d lambda. I have dl over d psi. Right, so this is to the power 1/2. So I have a 1/2. Everything goes down. So I have a 1 over 2l times minus 1 over c squared. And then what is left here, right? And I have it twice here because there's symmetric between psi alpha and psi beta, not that it matters. So I have a 2 times eta alpha beta d psi beta over d lambda is equal to 0. Now what is L? In reality I can write down L as d tau over d lambda. Right? Because of that. So here I have a d over d lambda of d tau over d lambda here. These are just constants, so I can just remove them. I don't care about them. L is d tau over d lambda, so I have d over d lambda of 1 over d tau over d lambda, so I can simply write this d over d. D tau over d lambda, so d psi over d lambda over d tau over d lambda, so I can write it down as d over d lambda of d psi beta over d tau is equal to 0. Right? Because I just use that here. And I multiply that again by d lambda over d tau to write down what? The usual one. D squared psi beta over d tau squared is equal to 0. Hey, we're familiar with that. What is that?
Newton's second law.
What?
Newton's second law.
Well, special relativity. That's the equation of motion of a freely falling particle in special relativity. Okay, not surprising. I don't know if you've seen that before, but freely falling particle, right, moves along a straight line, which is the geodesic equation. Now, if we got that properly, let's repeat the same calculation, but now for general relativity. Questions?
We usually use tau as a natural parameter, right? But here we choose lambda.
Lambda is a parameter along the world line. I take a path, can select tau, I want to minimize it, so I just have a lambda. Just for the calculation, it's easier.
Well, how would you do it for a photon?
What?
How would you do it for a photon?
Same thing. I can always select the parameter along the world line. Let's do it now in the GR formalism. Exactly the same thing. So tau from A to B is the integral from A to B of d tau is integral d lambda of minus 1 over c squared. Now I have a g alpha beta dx alpha over d lambda dx beta over d lambda 1/2. Identical. So the Lagrangian now, L, would be what is written here. Minus 1 over c squared, g alpha beta dx alpha over the lambda dx beta over the lambda 1/2. Lagrange equation of motion. D over the lambda. Now I have the L over the x over the lambda, so it's the same thing. So I have a 1 over 2L minus 1 over c squared 2g. But yeah, I switch because there is okay, sigma beta dx beta over the lambda. Yeah, it was just easier mathematically because I had to switch alpha and beta. Just use sigma. It doesn't really matter if it's typically alpha. But now I have. Now I had a 0 previously, right? Because I tried the L over the x. It gives me a 0. Now on the left hand side, on the right hand side, sorry. No, I'm not gonna get the 0. Why am I not gonna get the 0?
That's G.
Because of G. Because G is now a function of x. Okay, so what am I going to get? Minus 1 over c squared, 1 over 2L. Now I'll have a dg alpha beta over dx sigma dx alpha over the lambda dx beta over the lambda. So again, same thing that I had previously. Did I miss here? L we said is the tau over the lambda. So I can stick that in here. And I end up with a d over the tau. 2nc squared, 2nc squared go away. And I'm left with d over the tau of g sigma beta dx beta over the tau. Right, the tau over the lambda. Turn this into dx beta over the tau. And from here I have d over the tau. Oh, so this is the tau. That's okay. This is not good. I had to multiply. Sorry, twice. So I had to multiply that by the lambda over the tau. Otherwise, I would have a d over the lambda here still. So I multiply the lambda over the tau. This one. Multiply by the lambda over the tau. Two sides. So here I have a d over the lambda that turns out into even d over the tau. L is the tau over the lambda, so I end up with dx beta over the tau, so I'm good here. Here I have 2L, so that will turn this into dx alpha over the tau, and then I multiply by the lambda over the tau, so it will turn that into dx beta over the tau. So I'm ending up with, oh sorry, this 2 went with this 2 is still there. So I end up with 1/2 dg alpha beta over the sigma, dx sigma, dx alpha over the tau, dx beta over the tau. Okay, fine. Hope not many more mistakes. So I have 1/2 and 2. This goes down. 2 here is left. So minus 1 c squared, 1 over c squared. Wait, I have dg sigma beta. L is d tau over d lambda, so dx beta over d lambda turns into dx beta over d tau. I multiply d lambda over d tau, so that d over d lambda turns into d over d tau. That's here. Here I'm left with 1 over 2. L is d tau over d lambda. So dx alpha over d tau. I multiply again by d lambda over d tau, so dx beta over d tau. And dg alpha beta over dx sigma. That's fine. So, okay, now we have to open it up. So I open that one up, and the equation of motion now becomes, okay, I have two terms, dg sigma beta over d tau, but g is a function of the axis. So I write down dg sigma beta over dx mu over d tau, and then dx beta over d tau, plus the second term, which is g sigma beta d squared x beta over d tau squared. And I'm just switching that here, so I have a minus 1/2 dg alpha beta over dx sigma dx alpha over d tau dx beta over d tau is equal to 0. We're getting quite close. All right, I just open that into 1 and 2, and this is just moved to the left hand side, so I end up with a 0. Okay, we're pretty close now. Now there is a symmetry here. Okay, let's see what we have here. G sigma beta. So we have here, over here. Start with this one. So I have a G sigma beta d squared x beta over d tau squared. Now here I have a symmetry. Oh, sorry. So here. Beta. Okay, now mu is a dummy index, so I can change it into an alpha. Okay, so I have a dg sigma beta over dx alpha d tau, dx beta d tau. That's okay. But because of the symmetry, I can also switch that to, there's a symmetry here between alpha and beta. Everything here is symmetric. So this term I can write as 1/2 dg sigma beta over dx alpha plus dg sigma alpha over dx beta. And here I have minus dg alpha beta over dx sigma times dx alpha over d tau dx beta over d tau is equal to 0. And what is left is just to multiply by the inverse of g, right? So if we multiply that by g, I wrote it sigma rho, then what do we get? G sigma rho, G sigma beta, that gives me what?
Delta.
Delta rho beta. So what I'm gonna left with this term?
Exactly the same, but with rho.
D squared x rho over D tau squared. And when I multiply here with that inverse, what do I get?
Equation of function.
This is a what? With the inverse of G?
Five connection.
Let's find connection. Plus gamma rho alpha beta dx alpha over d tau dx beta over d tau equal to 0. Or if you prefer, d u rho over d tau plus gamma rho alpha beta u alpha u beta is equal to 0. Okay, now just one comment, right? If we talk about photons, for photons, d tau is equal to 0. We know that, so we cannot do that directly with d tau. But we can still use this parameter lambda along the path. So, but you can write x alpha is x alpha of lambda is always true. So we can repeat basically the same calculation minus the part where we switch between tau d lambda. And we end up that there is the same equation. We have d squared x rho over d lambda squared is minus gamma rho alpha beta dx alpha over d lambda dx beta over d lambda. This is known as the geodesic equation for now geodesics. Okay. What was the importance of this exercise? Why did we do it? What did we just show?
That they will always follow the path that we have time.
Right. Basically, we just show that. Remember this example? That's the example I always have in my mind, right? Of an airplane that is traveling through Earth. Actually, it's my mistake. I have a small globe. I wanted to bring the globe so you can see. Maybe just wait 5 more minutes before the end of the class and just go to the office and bring the globe so you see. When you are subject, when you're in a... Okay, let's stick to this example. We have an Earth, right? The airplane is essentially forced to move along the surface of the Earth. Although we can say our world is 3D, but practically planets only move in 2D. Right? Forget about going up and down. It's negligible relative to the side of Earth. Right? Planets are forced to move along the surface of the Earth, which is a sphere. It's a two-dimensional sphere. Right? And they will move along the shortest path. The shortest path would look exactly like that. So what we just proved is that every time we have space, really, the world is manifold. Every time we have a manifold which is non-Euclidean, has some force us to move. We have some restrictions. Then the shortest path between any 2 points on that manifold will be exactly this geodesic. Right? Of course, if we are here, New York is here, and we want to go from here to New York, right? Of course, the really shortest path is that. Well, we can't do that because we don't dig straight into the crust of Earth, right? So what we do, we'll go like that, And the shortest path would be exactly this geodesic which is described by. Okay? That's a simple example that can easily be visualized. Of course, when we go to higher dimensions, like 3 dimensions, 4 dimensions, it's much more difficult to visualize. Also, when we go to like strange spaces, it gets difficult to visualize, but mathematically, we just prove the equation will always hold. Right? Okay. The last subject I want to talk about today, before we move on to the next subject, is called the weak field limit, or the Newtonian limit. Any further questions about that? Before we move on.
Could you please write explicitly how G alpha beta depends on X alpha? Because in the last lecture, I guess, we said that the dependence is only by partial derivatives, not by coordinates.
Yeah.
Yeah, metric tensor, right?
Yeah, but the example I gave you, right? If you have coordinates of r and theta, right, in Euclidean space-time, G you knew was 1, 0, 0 r squared, right? So G theta theta is r squared, where r is the coordinate. Okay, that's the way to think of it. G here now depends on the coordinate.
Okay. I was a bit confused by
It's very good.
previous definition.
No, it's the same definition. I did not change the definition.
Yeah, but
Nothing will change. Okay, you have to practice it.
sure.
The reason we are associated with generalization of straight line is because for gamma equals 0, the solution for x is a straight line. It doesn't look like a straight line here.
It is a straight line.
How can I see it? I understand the math and I understand the trajectory. But why do we call it a straight line?
Wait for 1 second. I'll go to my office and I'll be back in 1 second.
Okay.
Maybe it will help you visualize it. I have a small Earth, which was slightly destroyed by human behavior in my office, but it doesn't matter. If you're an airplane, you're trying to fly from here to Tel Aviv, which is somewhere here, wherever, right? You can choose many paths, right? If I want to go to New York, I can go like that, go like that, go wherever I want. But the shortest path, if I want to go the shortest path, I'm subject to the constraint that I am forced to be moving on this 2-dimensional surface, right? I cannot go through Earth, okay? But on this 2-dimensional surface, if I want, what is the shortest path? The shortest path, it's also called the Great Circle. You might have heard the name. Just take a rubber, piece of rubber, put one side on point A, the other side on point B. Let's say I want to fly to Los Angeles, which is somewhere here. Right? So you see, which may look a little bit counterintuitive, if you're not familiar with that, that the shortest path from Tel Aviv to Los Angeles actually takes you quite close to the North Pole. Right? You can actually see, but you can only see that here, because if I draw this map like a two-dimensional, like they do in airplanes, right? Oh, this is getting broken. What you'll see, right? This is North America, South America, whatever. This is Europe, and Africa, and Asia, somewhere here, right? The shortest pass from here to here will go something that will go. Yeah, right? But this is just because this is basically proof that the two-dimensional surface of a sphere is not equivalent to a two-dimensional Euclidean space. That's known as a cartographer's problem. You cannot map at any point, all the points in the two-dimensional sphere to all points in the space. There's always at least one point which you cannot not map. Typically in the maps that we're used to see, there are 2 points, right, which people select in the North Pole and South Pole. But that is for our visualization. In reality, the path the airplane will take will be the shortest, minus constraints, I said. The shortest from wherever we are to wherever you want to go. And that, on this two-dimensional map, it could not like not make the shortest, but it is the shortest. But the only way of seeing that directly is if you take a globe, which is not being destroyed.
I cannot map it because the 2D flat map is finite, right? If I take
You cannot map it because they're not the same spaces.
But if I will take the Malbeno Zen, make it infinity, I can map it. How is it different from the Riemann split?
Mathematically, you cannot do that. There will be at least one point which you can never map into a point. Mapping is one point on that map and not another point on that map. I can go through the exact mathematical definition of that. For now, I don't want to do that for now because I think it will just confuse you. I think it's easier for you to visualize, and then we'll get into the exact mathematical definition. For now, the important thing is, how do you describe the path that an airplane will take? By this equation. You have to specify properly the metric on the sphere, which is not going to be that metric, obviously, because a sphere is not the same space as a flat space, Euclidean space. And then you can calculate all that and calculate the trajectory. All right? Okay, so I want to do one more thing. Let's do that. Let's call the Wickfield approximation or the Newtonian limit. So what I care about, we're going back to physics. What I care about now is to look at the geodesic equation and see what form it gets in the limit of weak gravitational field. Okay, that's my goal. Of course, what we really want is to get back Newtonian physics. Right? Otherwise, we're in shaky situation. So the idea is that if we go to the weak field, called weak field approximation, you'll see why, then we should retrieve back Newtonian physics. Let's do that. So what do we mean by weak field or Newtonian limit? What is Newtonian limit? Actually, three conditions.
Three laws of
What?
Newtonian physics, like first, second, third law.
Yeah, we're going to retrieve them.
Okay.
But what do I mean by the Newtonian limit, a weak field? What do I mean by a weak field? A Newtonian approximation.
its space will kind of flat
Yeah.
everywhere.
Yeah.
Not so curved.
Yeah, so there are three things. This is the second thing. That means the gravitational field is weak. It's weak.
We're very slow.
Meaning that, yes, very slow. Perturbation of flat space-time. The first one is that everything is slow. So, what means slow? Particle moves much slower than light. The second is that weak gravitational field, meaning that the space-time is flat with a minor perturbation. Not exactly flat, but close to flat. What will be the third one? The third one is that the gravitational field is not changing in time. It's static field. Right. It's not changing in time. So let's see. What do you mean by moving slowly? dxi over d tau is much smaller than c dt over d tau. So if we look at the geodesic equation, right, d squared x rho over d tau squared plus gamma rho alpha beta dx alpha over d tau dx beta over d tau equal to 0. What does that give in the limit? Since xi is much smaller than dt, right, then I can simply neglect everything which is not the 0, 0. So I'm only left with the 0, 0 terms. So instead of rho, I'll just write a mu, because I don't care. Right, so I can write down d squared x mu over d tau squared plus gamma mu 0, 0 c dt over d tau squared is equal to 0. That's the meaning that's slowly moving particles. Now we said that the field is static. What does it mean that it's static?
It's derivative.
The time derivatives of g, all the time derivatives of g, mu nu, vanish, right? So, all time derivatives of g mu vanish. We have all the relevant Christoffel symbols, gamma mu 0, 0, 1 half g mu lambda, d0 g lambda 0 plus d0 g 0 lambda minus d lambda g 0, 0 is just minus 1 half g mu lambda d lambda g 0, 0. Right? D lambda g 0 is d 0, 0 over d x lambda. You remember it. Okay. And then we said that the gravitational field is weak. What does it mean? If it's weak, that means that I can write down g mu nu as what? Minkowski, eta mu nu, plus some correction, h mu nu. What I mean by correction, it means that h mu nu in absolute value is always much smaller than mu. In that case, to the first order, what would be the inverse of the metric?
same.
No. Minus. H mu nu is eta mu rho, eta mu sigma, H rho sigma. So, if we plug it in here, we got that gamma mu 0, 0 is a minus 1/2 g mu lambda d lambda g 0, 0. G 0, 0 is eta 0, 0, which is just constant, so I don't care about its derivative, it's eta 0, and d lambda h 0, 0. Small perturbation. So, go back to this geodesic equation. And it takes the form d squared x mu over d tau squared is equal to 1/2. Actually, I don't need even the g, it's eta. Right? There is a small perturbation which is will be the second, give me a second order, so I don't need that. So I have a 1/2 eta mu lambda d lambda h 0, 0 c dt over d tau squared. Now, what is d0 of h 0, 0? What is d0 of h 0, 0?
0.
0. Why?
Because if it is
Because
static.
it's a static field. Right? So if I take the mu equal to 0 component, so this is 0, right? Mu equal to 0. What are we going to get? What is x mu?
Linear function.
T. Right? When mu is equal to 0. So what do I have here? What do I get here?
0.
0. So what do we get? D squared x mu, which is just t, over d tau squared is equal to 0. Which means that dt over d tau is constant.
Gamma, right?
What?
It's just gamma.
Just 1, because it's a weak field. Everything is moving much slower than c. Okay, so dt is equal to d tau. What about the space-like components? D squared xi over d tau squared is 1/2 eta inverse eta, right? Is just 1, 1, 1 on the diagonals. So di h 0, 0, and here I just have c dt over d tau. So this is c dt over d tau squared. This will just be 1s. Here it will be di h 0, 0. So we can divide that by c dt over d tau squared, which means that it will just mean that I am basically changing the derivative with respect to tau to derivative with respect to t. That's all. So we'll have d squared xi over c squared dt squared is 1/2 di h 0, 0. that already starts to look similar to what we're familiar from Newtonian, right? D squared xi over dt squared, right? This is just the acceleration. So what should be di h00? What should h00 be?
The potential.
Potential, right? Derivative of the potential is the force, right? So h00 should be the potential. So if we can write down what is left is to write down identify h00 as minus 2 phi over c, where phi is the gravitational potential. Then we have from here d squared xi over dt squared is minus di phi.
Shouldn't be
C squared.
C squared, yeah.
I put here c squared. H00 is minus 2 phi over c squared, right? So the c goes away, 2 goes away, and I have d squared is minus di phi. This is h. We said what is g? G is eta plus h. Right, so that means that the g00 minus 1 plus h00, 2 phi over c squared. Phi is just minus gm over r. Not too bad. What did I just show you? What did we just do right here? I looked at I looked at the Newtonian limit. Said, okay, I derived the geodesic equation. And I asked myself how the geodesic equation looks like, right, in the weak field approximation. And I define the weak field by saying there are 3 conditions. Everything moves much lower than c. Gravitational field is weak, namely the perturbation. I can treat the space-time as being in Minkowski with a small perturbation, and it's static, it's not changing in time. And when I did that, I showed that to a first order approximation, right, I neglected here higher order terms, I showed you that if I identify G00 to have this form, right, the other G's I don't care, that will be just eta, so it's just 1. But if G00 I have a minus 1 plus 2 phi, where phi is gravitational potential, I retrieve back Newton's equation of motion. It's really good. We know that we're in the right direction. The geodesic equation does give us back Newton's equation of motion in the right approximation. So we're definitely on the right track. All right, we're a little bit over time, I think, but not too much given that we started late. Any further questions? Comments, concerns, issues raised? No. Okay. So I think by now you start to see where this is heading. I think it will get slightly more nasty before things will settle down to don't worry. But so I'll put my lecture notes online so you can have a look at them if you know. But everything is from textbooks. You can just go plenty of textbooks, and it's all the same things. And make sure that you are, constantly follow what I'm doing here. It's very, very easy to get confused with all these indices and notations, but the important thing is not so much the indices. The important thing is to follow the logic, so that you understand why I'm doing what I'm doing, and to see that what we do is the right thing to do. right? Okay. Cool. So we meet again in 2 weeks' time. Then we'll have to go deeper into the concept of manifolds and how do we manipulate objects and manifolds such as vectors, etc.
So next week, Tuesday, will be no lecture?
Next week there will, so this Thursday is a holiday, no lecture. Next week there will be no lectures. We'll find time to compensate for these lectures. I'm not in Israel the next week.
Okay.
So there will be no lecture. I mean, I'll be available for emails if there is something urgent that you need to ask me or the homework.
Okay.
But I will not be present here, so I can leave the talk.
Thank you.
Alright, so see you again in 2 weeks' time and have a nice holiday.
שאלה. אני לא כל כך מבין למה אני לא יכול למפות, נגיד, מכדור הארץ למפה אינסופית. מה ההבדל נגיד בין זה לבין המיפוי שלבים של המשוך המבוקר?
כשאתה אומר מפה, אתה צריך למפות נקודה לנקודה. כל נקודה, פה אתה צריך להיות מסוגל למפות על נקודה בין הנקודה.